Welcome back. We're going to continue our studies of conic sections by exploring the hyperbola. And in real life, hyperbolas have many uses. You will see their uses in medicine. So think about like GE Medical, like an MRI machine and that kind of thing. You'll see them in satellite communications. You'll see them in headlamps of cars or your headlights, and also in optical. So you'll see uses of hyperbolas in many real-life situations. The objectives of this video, though, we're going to define the hyperbola, we'll explore and identify the equation of a hyperbola, we'll find the equation of a hyperbola, we'll look at the asymptotes of hyperbolas, and then we'll sketch a hyperbola. A hyperbola is simply the set of all points x and y in a plane for which the absolute value of the difference of distances from two distinct points, and those 2 points are the foci, is a constant. So we're saying that the absolute value of d2 minus d1 is some particular constant. And that would work for the other branch of the hyperbola as well. If we were to go to the other hyperbola and work with a couple of distances, d2 and d1, so the absolute, or I call it probably d3 and d4, the absolute value of d3 minus d4 is going to be some constant, and they're going to equal the same thing. We've got some vocabulary. We'll connect that vocabulary to the diagram here on the right. The branches of the hyperbola is the graph of the two disconnected portions of the hyperbola. The vertices, or the vertex, is the intersection point of the hyperbola and a line from the foci. So think the bottom or top of the, I have hyperbola here, but I probably should have branches. The top or bottom of the branches. Now hyperbolas, this one opens up and down. They also can open to the left and to the right. The transverse axis is a line segment connecting the vertices. So our transverse axis passes through the center here and connects the vertices of the hyperbola. And the center of the hyperbola is the midpoint of the transverse axis. And the center is the same distance from each vertex. That we call distance A. And the foci are also equidistant from the center. And that we call C. So C is the distance from the foci to the center of the hyperbola. The standard form of the equation of a hyperbola, this should look really familiar. It's going to look a lot like our ellipse, a lot like our circle. Well, we are working with conic sections, so there's definitely some similarities. We have two different standard forms depending on which way our hyperbola opens. If the transverse axis is horizontal, meaning our hyperbola is going to open left and right, we have x minus h squared all over a squared minus y minus k squared over b squared is equal to 1. And then the y's and the x's flip. The a's stay where they are. So we have y minus k squared over a squared minus x minus h squared over b squared equals 1. And that will be a hyperbola where the branches open up and down, or our transverse axis is vertical. So we lead with our y squared, and our transverse axis is going to be, kind of looks like the y axis. So this equation only differs from an ellipse by the subtraction of the two fractions. And we will also use c squared equals a squared plus b squared. Now remember, in the ellipse it was c squared equals a squared minus b squared. So I say they're opposites here, but the only thing that changes is that plus sign. The vertices are a units from the center, and the foci are c units from the center. And we saw that in our previous diagram here. The vertices are a units from the center, and the foci are c units from the center. And we can use that then to calculate b if we needed to. And the formula, if the center of the hyperbola is at the origin, is just we don't have our h and k anymore. I don't think I mentioned that in here. Probably one of our notes is hk is still the center of our hyperbola, just like in a circle, just like in our ellipse. And if it's centered at the origin, we have x squared over a squared minus y squared over b squared equals 1. So that is going to open to the left and right. And then we could also have y squared over a squared minus x squared over b squared equals 1. So notice that the a squared is always positive. So that's something to keep in mind as well. A squared is on the positive. So we're always going to kind of lead with the a squared in our denominator in the hyperbola. I think in the ellipse, the a squared and the b squared could flip. So here you go, a couple samples of what it looks like with our transverse axis being on the horizontal. So here's the example of that, where we're leading with our x, our perfect square trinomial with x minus h squared, and our transverse axis is horizontal and our hyperbola branches open left and right. And then here we lead with our perfect square trinomial y minus k squared, still all over a squared, but now that transverse axis is vertical and that hyperbola, the branches of that open up and down. Objective 3, finding the standard equation of a hyperbola. Find the standard form of the equation of the hyperbola with foci at -1, 2, and 5, 2, and vertices at 0, 2, and 4, 2. Because our y-coordinates are the same in both our foci and our vertices, we know that this hyperbola opens along the horizontal. It's going to open left and right. If I were sketching a diagram of this, and just with our information given, we have foci at -1 on the x, 2 on the y. Vertices are at 0, 2, and 4, 2. Branches are going to open something like that. We can use our midpoint formula to calculate the center, and because we have the foci and the vertices, we can use either point. We're going to get the center no matter what. So if I use my foci to find that, I just take -1 plus 5 over 2 and 2 plus 2 over 2, and my midpoint is at 2, 2. So now I have found my h and my k are both 2 and 2. So h equals 2 and k equals 2. Since the vertices are a units from the center and the foci are c units from the center, I can use c squared equals a squared plus b squared to calculate b, or the denominator. So I've got my center here at 2, 2. I know this distance here is c. I think that's 3 units. So I know my c is 3, and my a value is here, and that is 2 units. So a is 2, so I can just calculate my b. 3 squared equals 2 squared plus b squared. 9 minus 4 is 5, which is our b squared. The square root of 5 is our b value. Substituting in the values we have for a, b, h, and k, with h equal 2, k equal 2, a equal to 2, and b equal to the square root of 5. We transfer that all down, and since our hyperbola branches open left and right, we're going to lead with our x minus 2 squared all over 2 squared, or 4, and minus y minus 2 quantity squared all over the square root of 5 squared. So we have a squared and b squared. Or squaring both of those, we get the equation of our hyperbola. One thing that's unique about the hyperbola is it's its branches will head towards an asymptote. So each hyperbola has two asymptotes that intersect at the center of the hyperbola. The asymptotes pass through the corners of a rectangle of dimensions 2a by 2b with its center h and k, as shown in the figure. So this a and b, we can get those from our formula if we need to. Here's just a picture of one. So they've drawn the box for us. Now remember, A is the distance from the center to the vertices. So if that's A, this whole length here is 2A, and our whole length on the left and the right of that rectangle is 2B. Our asymptotes have equations, and it depends on if the branches of the hyperbola open along the horizontal or the vertical axis. The thing that changes here is essentially our slope gets flipped. So our equations, y equals k plus or minus b over a times x minus h, if the asymptotes are on the horizontal transverse axis. And same equation, but our slope becomes a over b if the branches of our hyperbola are on the vertical axis. We will use those later on, so keep those handy. So let's go ahead and sketch a hyperbola of 4x squared minus y squared equals 16. We'll divide both sides by 16 because we want this to be equal to 1. And the 4 over the 16 simplify just to 4, which is 2 squared, and our b value here is 4 squared. So we know that since x squared is positive, the transverse axis is the horizontal axis, and this is going to open to the left and to the right. Our a value is 2. Our center is at the origin, so 0, 0 is our h and k. And since our a value is 2, we know then that will give us vertices of negative 2, 0, and 2, 0. So our hyperbola is going to look something like this until we draw our box. The endpoints of the conjugate axis is 0, 4, and 0, negative 4. Well, that comes from our b value, right? Our b value is 4, and since box for our asymptotes is going to look something like this. So we construct the box for our asymptotes, and we've got that diagram down here on the left. And this, we can construct our asymptotes. We draw our asymptotes through the center of our hyperbola, and then we can draw our branches. You can also use your graphing calculator to sketch a hyperbola. And as we've done with our other conics, we'll solve the original equation for y squared. And then we have to square root both sides and do our plus or minus. And then we graph both versions of y equals. So we're going to graph kind of a y sub 1 and a y sub 2. One for our plus and one for our minus. So in our last problem here, we had 4x squared minus y squared equals 16. I'm going to solve this for y squared. So it looks like we're going to add y squared and we're going to subtract 16. So here we go. We square root both sides. We get plus or minus the square root of 4x squared minus 16 equals y. So our y sub 1 would be the positive version. Our y sub 2 would be the negative version. We view them in the same viewing window, use a square setting, and you'll get a nice diagram of your hyperbola. And we'll get some more practice with hyperbolas and graphing them when I see you in class.